Let us warmly welcome architect Nirodha Gunadasa, the Vice President of CTBUH Sri Lanka, to the stage. His opening remarks promise to provide us with valuable insights and perspectives that will guide us on this intellectual journey.
Right, okay, so my duty is to give the introduction to the theme this time. So let me begin with a question that terrifies CTBUH. Why do you need these tall buildings? Why do you need them? Can't we all live like this, all of us? What do you think? To the horror of our CTBUH chairman, the answer is yes. Yes, we all can live like that. We don't need all those tall buildings, but that is 100 years ago, not now. Today, if you think about it, there's no way to do it. But what's the difference? Actually, 100 years ago, majority of the world population lived like that. So why can't we do it today? So this is the place we live, our planet. And 100 years ago, we had 2 billion people living here. Just the right number of people fitting to this particular planet. And it's like having a 2-bedroom house and having 2 people to live. Each one can have a single bedroom. But what happened today? Today we have 8 billion people living in this world. And it is estimated by 2100 there will be 11 billion people. So when you have a 2-bedroom house and you have 11 people to live inside that, you have to change your strategy of living. Right, so if 11 billion people start to live like this, if 11 billion people start to live like this on this planet, it will take up massive amount of natural land and massive infrastructure networks are required. And there will be a climate crisis just because of that. Okay, so the good thing is, as Mr. Shuramal also pointed out, the mega cities of the world are at a tremendous growth today. So these are some of the mega cities. So he showed what's happening in Colombo, but if you look at even New Delhi from 2011 to 2024, there has been 43% growth in New Delhi, and there has been 53% growth in Dhaka, and we have Beijing 44%. Even the developed countries like New York, we have 20% growth. So mega cities are at tremendous growth. And billions of people are today moving into cities. It's a good thing because knowing or unknowing, by doing so, these people are contributing to make our world a more sustainable place. So this is the world urban population. By 1980s, we had 1 billion people living in cities. And 2015, or right now, we have more than 3 billion people living in the cities. And it is estimated by 2050 we will have 6 billion people. Look at the numbers, 3 billion now, 6 billion in just 25 years. So by 2050, we need cities for 3 billion more people. Right now we only have 3 billion and we need cities for 3 billion more people. So it's just doubling the global urban population. And few people understand that this is the biggest force working on Earth today, the biggest force. All these bright dots in the world is a city, and they are going to be double in size and grow twice in just 25 years. So it's the biggest movement on Earth, and as professionals we have to make sure that we do it in a sustainable way. We direct these people, settlements and all in a sustainable way. Unless we do that, there's a problem. So we need cities for 3 billion people and we have to get it right. So unless we get it right, so if we are not going to get it right, all these climate solutions we are talking about, we have the green building chairman here, all those solutions we are talking about are not going to save the planet. So this is the most important thing, right? So we need sustainable urban planning. And we cannot think about cities two-dimensionally as earlier we thought. Just plans. We have to have 3-dimensional plans for cities. We have to use the vertical axis and we have to go tall. There's no other option. So that's why we need tall buildings today. So he's now happy. Okay, But the second question is, okay, we can go high, but how tall can we build? How tall can we build? What is the maximum limit? This is a 10-meter tall building. It's 10 meter by 10 meter cube. So if I make this 10 kilometer by 10 kilometer by 10 kilometer by cube, I think everybody agrees with me. In this small cube, 3 people can live happily. It's a big cube. So if we scale it up like that, I think we can house all these 3 billion people we are talking about. So it's big enough to do that. But can we do this? Can we build this kind of a cube? Is it possible? It cannot be done. Why? It cannot be done due to a very, very fundamental basic reason. I'll explain what it is. So this is a simple cube. Its lengths are 1, whatever unit, it doesn't matter. And its density is 1. So the weight of this cube, I think everybody can calculate it. It's 1 by 1 by 1, that is the volume times the density. That's the weight of this. And I'm talking about this base area of this cube, which is 1 by 1, it is 1. And I'm interested in the pressure. What is the amount of pressure that is going to be there at the base? So it's the weight divided by the base, and we get 1. What happens if I scale this up? If I make this bigger, 10 times bigger, let's say. If I make this 10 times bigger, the length 10 by 10 by 10. And if you make the same cube at the same material, its weight is going to be, I have to press this hard, isn't it? Yeah, it's 10 by 10 by 10 times 1,000. But the base size is only 10 by 10. So what happens? The pressure becomes 10. So you can see the same material, same structure. When you just scale it up, you get 10 times pressure on the base. So when you have this 10 meter building, when you scale up to 10 kilometer thing, what will happen? We will have 1,000 times more pressure. If this is a concrete building, these foundations are going to have 1,000 times more pressure. So what happens? These things collapse. So we can't construct such buildings. I think you have played with these glass balls when you are small. When you drop it on a cement floor, it it bounces up. What will happen if you drop this kind of a glass ball? It smashes into pieces. Why? Just because it is big. So this we can see even in nature. So when you look at an elephant like this, it has such a huge legs. And a deer doesn't need that kind of legs just because the deer is little small. And if you take an ant like this, it has this tiny little feet. So if you scale this ant to the size of an elephant, if you make this an elephant, this elephant will never be able to get up this tiny little flimsy legs. So scale matters. So even if you look at a building, it's the same thing. So 1 meter building, I think you have made models like this at the university. You can make this kind of a fancy model, but you can't do it at 100 meter height. It collapses. Right. So therefore, designing tall is not easy. It's a difficult thing. Okay. So the reason is tall buildings. When we are talking about tall buildings, we are working at the threshold of collapse. That's the important thing we have to notice. And I think we have Professor Ranjit here. He's I have to go back, isn't it? He's the king of biomimicry, isn't it? So your students come to me and then say, why don't you design buildings like this, tall buildings like this? It has a lot of views, lot of social interaction, everything if you design a building like this. Now you know why we can't build tall buildings like this. They collapse. So I like to design this kind of a building. This is a stone I have seen in Savannah. So we can't design buildings like this. It's difficult. So if I were an ant, I would have designed a tall building like this. But at this scale, it collapses. And I love to design buildings like this tall building. It will be very fantastic, but we can't design buildings like that. They collapse. So architect Ransafiano says, architects spend their entire lifetime with this unreasonable idea that you can fight against gravity. So people who know that, they don't go to do that. Right, so architects can't do it. So these kind of things architect can't do. So 1,000 kilometers, this 10-kilometer building nobody can do. But we have people who can do, let's say, 1-kilometer building, because breaking this pressure barrier is possible. So for example, now today we are bringing Professor Priyan Mendis, who is an expert on that, who is a world eminent scientist who has discovered high strength concrete to design foundations of tall buildings, and he has contributed to do many world class buildings. So that's why I just pointed out this. So that's the physical limitation of designing buildings, the physics limitation. So clever people like Professor can handle that a little bit. But the thing is, that's not the real limitation in tall buildings. In the tall buildings, we have the efficiency limitation, or the most importantly, I call it the sustainability limitation. So what is this efficiency limitation? Something important to understand, very important, so I will go a little deep into that. So just think a tall building as a bottle like this. This bottle we have to fill. We have to fill it and also drain off. Fill with what? We can fill with people, we have to fill it with water, and we have to drain off sewer. That's what we are doing with tall buildings. And the challenge is we have to do it in a given time called T. Because my building is very tall, I am not going to go to the lobby and wait for, let's say, 10 minutes till the lift comes, because I understand, I respect it's a tall building. No. Everybody wants to go to their office in 2 minutes, regardless of the height of their building. So T is a constant, we can't change it. So this is the bottom area of the building. So let's say cross-sectional area, I call it capital A. And let me number this. First floor, second floor, third floor goes up to nth floor. These are the floors of the building. And then the volume we have to fill is A times n. It's clear for you, isn't it? This is the inlet of the building. So you put things inside that. That area I'll take as A. And the speed we pump things up, I'll take as V. So our flow rate is A times V. It's clear for everybody, I suppose. But there's a little difference in a bottle and a tall building. There's only one difference. There is a central core. So you don't fill it like a bottle. You bring things through the core and then fill in. So it is not correct to say that A times N, this is the area to fill, volume to fill. It has to be A minus this little A times N, because we are filling only the sides. So you can now calculate the time to fill the bottle. It's very easy. It's the volume to fill divided by the flow rate. It's A minus A times this thing, the top thing divided by the bottom thing. That's all. It's very simple, isn't it? Everybody can understand it. So let me keep this, I'll take it up and keep it up there. So I have just changed the order of it. I have taken the A out. It's a simple thing I'm explaining. So I just talked about this because I want to explain you what is the efficiency of the tall building. It's something very important. So the efficiency E. Efficiency is, I don't know if this is the bottle, the total area to the usable area ratio. Yeah. So it is the usable area divided by the gross area, and it is A minus A divided by A. So I'll just simply take that A I have calculated up there and I'll put it here. And then we get a very simple equation like this, E equals Vt over Vt plus N. It's a very simple equation. You can work out the workings. I'm not going to do that, so you have to believe me that it is so. So what does this equation tell us? It tells us something very, very important about tall buildings. When the N increases, the efficiency goes down because they are inversely proportional. That's something simple. When you look at this, you can very simply understand. As the height of the building goes up, tall buildings become gradually inefficient, little by little. But that's not the most important thing. There are other important things you can look at when you look at this and see. Where is this A we were talking about? The cross-sectional area. It's not there. So what that means? So it regardless you are having very large land, you are building a tall building or a small land, it doesn't matter. Efficiency is efficiency. So whatever the building you build, efficiency is going to go down. It's a very drastic thing about tall buildings. And then this is something very important. How to increase efficiency then? If you are going to do a tall building, only way is we have to work with this thing called Vt, whatever it is. But T is a time, V is a velocity. We bring people, water kind of things up the buildings. And thing is, here we have to increase it substantially because this Vt is upstairs and also in the denominator. So it's not a direct relationship. So we have to increase it sufficiently and substantially, and that is something not so easy to do. It's very difficult to increase the efficiency. So if you want, I can calculate this Vt very easily in front of you. What this Vt is. So these are the tallest buildings in the world. I think you know it. Let me keep this Burj Khalifa out of the picture for a while. And then all these buildings, they have 97 floors, 111, 93. I'll take it as 100 floors. And I know the efficiency of these buildings are about 50 to 60%. I'll take it 50, and then when you put these numbers, I get a number for Vt. It is 100. It's a very simple number. And now you can use this and, for example, calculate the efficiency of a 150 floors building. If you put the numbers, you will see it's only 40% efficiency. Burj Khalifa, I left it out because its form is different. It's a cone form. Actually, its efficiency is much less than a normal tall building. A professor has worked on this. The thing is, this top part, if you calculate it, it's highly inefficient. So it's not a business sense building. It's actually a cultural pride. So just to say we have the tall building in the world, it's done like that. So in simple words, we'll just forget mathematics. This is what's happened. This is your building, and this is your competitor's building. Two buildings, the same usable area, and you save from the land. When you're doing a tall building, your competitor is using a large amount of land, and Shirom will explain that. You are using only less amount of land. But you lose from efficiency. So that's the problem we have. And when what you lose is much more than what you gain, you lose. It's so simple. You lose in terms of business, and you lose even in terms of sustainability. So that's the failure of tall buildings we see. And although we boast CTBUH also about tall buildings, the super talls always fail. So we have a Nakheel Tower, 200 floors. Professor, is it started construction? No, just on drawing board. Yeah, we have the Sky City Japan, 196 floors, just drawing board. Just nothing has happened. And we have Jeddah Tower, they started, they did the foundation, stopped, and then they restarted, and once again, they have to stop it. We have Dubai Creek Tower, 160 floors, started, and I'm not sure that it's going on. It's stopped as far as I know. And I can show some examples in Sri Lanka as well, but I shouldn't do that. So there are a lot of projects like that. So as far as we know, the super tall always fail. The reason, I think most of the people in the world doesn't know, but now you know what the reason is. Okay, so going vertical is a challenge. So that's why I just explained this. It's a challenge, and that's why we brought an experienced person like Adrian to tell us how to face these challenges in tall buildings and also convert these challenges into opportunities. So we were talking about this efficiency limitation. Is this an unbreakable deadlock? So as human beings, can't we build more than 150 floors? Are we stuck there? How to break this barrier? I think it's possible to break it. There's a way of doing that. The problem we have is we are always thinking about having the inlet down there. That's the problem. So it need not to be there. It can be up there or even up there. So let's think this is a set of tall buildings, and this is the notion of ground. It need not to be down there at the bottom. It can be up there. And what do you mean by the ground? What I mean by ground is where I go home, where I go down to go home. It need not to be there. It can be somewhere up there. It is where I run when there's a fire. So it need not to be there. And it is where all the services come. So it can be here or there, wherever it is. So that's the concept behind this Moshe Shabdin's concept of future city. It's a very popular concept, but it never built because I think he didn't justify it so well like I did today. Otherwise it would have been built. So the idea is you have grounds at several levels. Here you have a ground level, up there you have a ground level where you go out, where you play, you have trees, you have roads, everything. So it's a multiple layer of city. So the way to go high is not individually building tall buildings, but as a city together we have to grow. So that's the way to go up. So we have even better vertical visions. For example, this Paul Bridge in 1982, he proposed this thing called the orbital ring habitat, where we have 500 kilometers away from the Earth's surface, there is a ring like that connected to Earth with space elevators like this, and people live there. It's a great vertical vision. So the idea is, I think those who know physics know it will collapse, but it doesn't fall down because it's not in the geostationary orbit. But with active means, it is stabilized with this kind of fast-moving trains kind of thing. Because of the centripetal acceleration, it's not falling down. The idea is everybody, we move there and we leave the Earth for animals and natural habitats. Orbital ring habitat is not just a fancy dream like the space elevator kind of thing. This is a thing practically possible. If you calculate it, it can be done. The thing is whether we have the motive to do that. So in future it might happen, I don't know. But it's a great vision. So it will be the next leap of vertical vision of humanity. But we have, I think, greater visions. So people talk about Dyson sphere, where people build a structure right surrounding the sun and capturing the entire energy output of a sun. So that is far away in future. It might happen. So we'll come down to Earth today. We have a problem today. We need cities for 3 billion people, and we have to get it right. And going vertical is an essential component of doing so. So that's my introduction to the theme, the vertical vision. Exploring the future of high-rise architecture. So we have several eminent speakers to talk about it, and there's no one to talk about the second part, its role in sustainable urban development. That's what I did. Okay, so that's it. So as CTBUH, we always make sure when you come here, you go home taking something that you beyond your expectation. So I think we will deliver it today. Our eminent speakers will do that. So that's it. So thank you very much.